Okay. So today I will continue along the lines that Fabio discussed last week. So before that, this announcement. So starting this Wednesday, the Wednesday meeting that this week is for the mini course, in general is for the seminar, starts at 3 instead of 3:30. So okay, up there some reminders about what was discussed last week. So we are considering interacting dimer models on a square lattice. So up there there is a reminder of the kind of coordinates we use. So we color black and white. So the black are the full, maybe full and empty. So the full will be called black. Black and white, the sides of the bipartite lattice we are considering. We attach coordinate x for the sides of the black sublattice. So notice that the black sublattice is a square lattice tilted 45 degrees compared to the original one. So once we make this choice, it's natural to use these coordinates E1, E2 for describing the lattice of black sides. And the white sides are labeled with the same labels, with the convention that the white side immediately to the right of the black side has the same coordinates. And then we will, in a second, we will associate Grassmann variables psi plus x, psi minus x to the black and white sides correspondingly. So we will study the model in a finite box that for convenience is chosen to be a square box. Doesn't look much square. Okay, it should be a square box of sides L and L by L in the E1, E2 directions. Okay, in the general case, even though we will simplify to a special case soon, the general case is defined as a interacting deformation, a perturbation of a standard dimer model with weights T1, T2, T3, T4 on dimers of the four kinds R equal 1, R equal 2, R equal 3, R equal 4. So there is a reminder. The elements of the Castellan matrix are reminded there. They are not exactly, again, there are four different values of for the Castellan matrix corresponding to the four types of bonds we have. They are almost the T1, T2, T3, T4 modulo these prefactors I minus 1 minus I appearing in R equal 2, 3, 4. So what was discussed last week by Fabio is fermionic. Yes.
Yeah. So M is the notation for the configuration of
exactly.
the dimers that you put down.
Exactly. Yes.
Yeah.
So this is the generating function for dimer correlations for our interacting model. It looks like this. So it's a sum over allowed dimer configurations in my box L times L. There is a sort of one-body prefactor. This is a product over the edges covered by a dimer in the dimer configuration M of the dimer weight TE, here modified by this exponential of the external field AE. This is just an additional field that one introduces so that if you derive the log of this with respect to A and then take A to 0, you get all the connected dimer correlations of the model. And here there is a multi-dimer weight, so an additional Gibbs weight that is called the interaction. So this is of the form e to the lambda something. This something, so lambda is a parameter that you should consider as a small parameter, and Wm is any local translational invariant interaction. And translational invariant here refers to translation of the lattices of the black lattice. And so what Fabio discussed last time, well, actually computing V only for a special case, but we soon will specialize exactly to that case, is a fermionic representation or Grassmann representation of this formula. This is an exact representation valid for any finite box. So this becomes Grassmann integral of this exponential of Grassmann function. This function has the following form. So there is a term that is the reference, if you like, quadratic part of the action. It corresponds to the solvable dimer model. Is written in this form. So it's the sum over all the edges of my box of this Grassmann bilinear function e of the edge, modified by the presence of this external field, plus an interaction. This is over the lambda. Now the lambda in this convention is reabsorbed inside V. This V is just the counterpart of this lambda W in the fermionic language. Last week it was discussed explicitly only in a special case that I will now recall. Here, let me stress that this E of the edge is the Grassmann counterpart of the, if you like, of the dimer characteristic function. Is defined like this. Is the product of psi plus psi minus at the two vertices of the edge. Here x is the label of the black side and y is the label of the white side, exactly as recalled above. And k of r is one of these values. R of xy is just the type 1, 2, 3, or 4 of the edge xy. Okay, and this v, it's important that it's at least quartic. It's quartic plus possibly additional higher order terms in psi. So let me from now on specialize to a specific case. So let me choose the TIs all equal to 1. So we are able to treat also the general case, but for the purpose of these lectures, I will restrict to this simple case, and I will restrict to the simple choice of interaction equal to sum over even phases of the indicator function of having two dimers like this at the two boundaries of the phase, plus the indicator function of having two dimers like this. So the even phases are phases of this form. Are the phases that have the black side, the full sides on the left bottom corner. So this is x plus e2, and this is x minus q. Questions?
I guess the sign of lambda doesn't matter. You can
No, it doesn't matter. We can, yeah,
college.
exactly. Yeah, and this is the dimer representation of the 6-vertex model. So this is an exactly solvable model by Bethe ansatz, but we will not use the exact solvability structure, and actually our results are valid for general interactions that are just local and translational. Okay, so in this special case, let me just explicitly write the z, and again for for simplifying as much as I can, let me restrict to the case of partition function. So I set the a is equal to 0. Possibly in the next lectures, if I have time, I will comment about what happens if I have the a's. So I just write, I set a to 0 and I drop the L index, so I just write z lambda. This becomes explicitly, it becomes the following. So it's minus, so here I just, if a is equal to 0, I just get minus sum over e of these things here. So this is just psi plus. So this is a notation that also Fabio used last week. And then I have the interaction. So the interaction is simply the of the following form. So it's plus alpha sum over even f, even phases of where in this notation, if this is the phase f, I'm calling E1, E2, E3, and E4 these phases here. Okay, so this was the result of a computation last week. If you like, you can just write explicitly in terms of the psi fields what this interaction is. If you do that, you get a very simple formula. You are invited to check. So you just simply get, actually these two terms are the same, so you get twice the same expression, and the expression is just minus the product of the fields in a specific order. Psi plus x, psi minus x, psi plus over x plus e2, psi minus x minus e1. So this is the interaction. So it's a quartic interaction. So let me. Okay, so later I will just erase the expression in terms of the e's. So you see that the partition function we want to compute is as a Gaussian reference part. Alpha here is just e to the lambda minus 1, so it's essentially lambda. So this is like so there is a Gaussian part minus lambda psi to the 4. So it's a sort of Grassmann fermionic analog of 542 theory, if you like. So we are in 2 dimensions, so we have a quartic interaction. The reference Gaussian measure has a specific specific structure that can be read from the covariance. Yes.
Does it have some? Does it remind you of the Tiering model?
Sure. Yeah, I will use this. So that I hope I will get there this week. So the multi-scale analysis of this object will be possible precisely because we will control the flow of the renormalized parameters by comparison with the infrared part of the Tiering model or lattice model. But this is notice that okay, this special interaction is solvable by Bethe-Assas, but not by bosonization. These again comments for those. So the simple bosonization solution a la Mantis Lib is or other people it breaks down because we have a lattice. So it's not exactly solvable by bosonization at finite lattice. Okay, so I will.
So the x's are running over the black sites and the...
No, yeah, you should imagine that x is just, so there is just one lattice that is tilted, yeah. So it's, yeah, if you like, the lattice of black sites.
Yeah.
Just rewrite it here.
Unfortunately, there are 2 x's. One is right, one is left in the figure.
Oh.
One is plus, one
And so I will actually it's convenient to analyze this. It's convenient to normalize to the non-interacting partition function. And in the following, I will call this normalized reference Gaussian integration. I will denote it by P psi. So this is a reference. So this with this notation, this becomes integral P psi e to the minus 2 alpha something like x. Okay, so this reference Gaussian integration is associated to the following covariance. So the covariance is nothing but the inverse of the Castellan matrix for actually just for the common habit for us at least is to call it G because this is like a Green's function for our problem. And this is explicitly dk over 2 pi squared e to the minus ik x minus y divided by mu of k. And mu of k is nothing but the Fourier transform of the Fourier transform of this the kernel of the Fourier transform of that quadratic part. So if you like, it is the Fourier transform of the Castellan matrix in the situation where all the t's are equal to 1. So mu of k is just 1 plus I e to the I k1 minus e to the I k1 plus k2 minus I e to the I k2. Okay. So this is it. Infinite volume, this is just a Riemann sum of this integral. We always write integrals. But you should remember that if you are in an infinite box, here there is, if you like, this is actually a Riemann sum, and there is a sort of infrared cutoff at the scale set by the whatever the usual pi over L appearing in the Riemann sum approximation of this. Okay, so this is an important rule, and the other important rule is the action of this integration on monomials of higher degree in the Grassmann variables. So this is also something that Fabio discussed. So if you have something like this, the rule to compute this is the same as for Gaussian integrals, but you have to remember that these Grassmann variables have the important feature that they exactly anti-commute. So if you exchange the order, you pick up minus signs. In order to compute this, you have to sum over all possible pairings of a plus with a minus. Reorder them so to put the plus immediately to the right of the minus it's contracted with. You pay the minus sign coming from the permutation, and then you replace each pair by the propagator. This is the rule. And the compact way, so this is called the Wick rule, fermionic Wick rule. It's the same as for standard Gaussian integrals, but there is this additional minus sign when you take the permutation. And the compact way of writing this is in the following way. It's just determinant of gx I yj with I j from 1 to n. Okay. So for standard Gaussian variables, you would have a permanent instead of a determinant. But besides that, so the reason why it's convenient to introduce this notation is that there is this, from a computational point of view, there are these easy correspondence rules with the analogous rules for Gaussian integrals. Okay, so some properties of this mu. So since okay, the properties of the mu, of course, will have an impact on the computation of the partition function, because now you see the interaction, this quartic interaction is just so exponential of sum of monomials. If you want to compute the a priori formal power series in alpha, you just expand in Taylor series the exponential. Each term in the expansion is the average of a monomial in the Grassmann variables, and the average of each monomial is computed using this rule. So if you want to understand whether your partition function, or better, the log of the partition function admits uniform bounds as L to infinity, you have to say something about the decay properties of G. And the decay properties of G depend on the singularity structure of mu. So mu, you can check that mu 0, 0 is mu for pi is equal to 0, and these are the only zeros of mu. And I will denote by p plus 0, 0, p minus pi pi. And I will need in the following also the behavior close to the zeros. So you can check that you get the following. So this is the behavior, and maybe you may find the more so the linearization produces, for those of you who know the matter, the usual Dirac operator in variables that quite naturally are tilted 45 degrees compared to the usual one. So it's a sort of lattice approximation of a Dirac propagator, this thing here. This comment, if you don't know what is a Dirac propagator, you just so this is the behavior. So this means that G decays like 1 over distance as x minus y, with a specific structure that was already introduced by Fabio last week, and I will come back to it soon. So to be precise, if you really want a behavior like 1 over distance that is representative of a scaling behavior, in the sense that if you derive, you get 1 over distance squared and so on, you have to extract some oscillating factors. So I will do that soon, but for the moment let me just observe that since this is a two-dimensional Fourier integral of something with simple pole singularities, this in real space this is like 1 over distance. Okay, okay. This kind of slow decay of correlation to large distances, or similar the singularity, the presence of singularities in Fourier space, implies that the formal power series that I mentioned for z lambda over z0 is affected by certain singularities, some of which were already anticipated last week by Fabio. let me just come back for a second to this singularities. So what we're interested in is the computation of this of 1 over L squared the log of that. This is the free energy or pressure, whatever, of the model. This in informal power series is obtained by the following procedure. Again, you should just expand in the exponential in Taylor series and then use systematically this rule. When you take the log, you have to use the miracle that was already mentioned last week, that when you perform the contractions, you should only retain the connected contractions. So the rule for the formal power series is to do the following. So you take 1 over L squared sum over x1 xn. Then I draw the expectation of the following object that I just draw graphically. So this object is what? Is this sort of plaquette interaction that is written there. So this is a symbol for psi plus x1, psi minus x1, psi plus x1 plus e2, psi minus x1 plus e2. This is what you get. Here I'm missing an factorial.
Also the sum over n.
Also?
The sum over n.
The sum over n. Yes. I get 1 over L squared, sum over n equal than 1, sum over x1 xn, alpha n over n. Okay, and the rule is that to compute this expectation. So here is the symbol that was introduced by Fabio. The semicolon reminds that you should only retain contractions that produce connected graphs. So something of this sort. Each field, each Gaussian variable should be connected with something else. Okay, so if you do something of this sort, you produce diagrams that are problematic as L to infinity. So this shows that there is no hope to prove naively that perturbations, this perturbation series is convergent uniformly in the limit L to infinity. If you want a non-uniform estimate, it's relatively easy, and I hope to get to the point today. So this is an example that was already mentioned last week by Fabio. Let me recall it and add some more details about this example. So this example, this is a possible. Here each of these vertices is just, I just didn't write this plaquette every time. I just drew a simplified version of the vertex. And I contracted these vertices in a special way. So I put, I contract each neighboring pair in this way, and then I attach this with the next one. And I produce a chain of objects of the same form. So this is one possible contribution to this guy. And already this guy has problems. So let me. So this guy is if you think for a second, you're invited to make exactly this computation. So you get such a simple expression: f of p is just the is just the Fourier transform of the value of this object here. So which I can also write in a very explicit form. So if you're interested, this is just exercise. This is just e to the. I hope I didn't get these factors in the numerator wrong. Mu k, mu q, mu k plus q minus p. K plus q minus p. So, what is the rationale behind this? So, these objects at the denominator are just 1 over mu, the Fourier. Should I rewrite it? The argument of this is k plus q minus p. So, here you have 3 propagators, each of which gives 1 over mu at the proper momentum. And in the numerator, you have the Fourier transform of the kernel of this guy, which is not exactly 1 because you have these shifts x plus e2, x minus e1. So you get this. So this is something very explicit. And now you start to worry because you see mu of p both in 0 and in pi pi as a simple pole. So for instance, the behavior around 0 is 1 over p to the power n, which is not integrable at p equals 0. Again, of course, if you are in finite volume, this is Riemann sum with a small cutoff, but the value of this in L is wildly divergent as L to infinity. So you don't want that. You would like to prove that this thing is uniformly convergent as L to infinity, and if you look naively at this, you see troubles. Okay, but now, so this is maybe too naive because this neglects the f of p upstairs. So if you're lucky, f of p has a 0 that cancels mu of p. So this you should try it. So if you do it. Okay, you sit down patiently. You have to be quite patient. And you check that f of 0 is equal to 0. Okay, try it. I tried, I knew it, but I checked this week and I lost too many hours. But it's a trivial exercise. So, but you're invited to do it. I mean, you get a bit crazy because of the exponential upstairs, but it's relatively easy to stay. So, okay, this is good. So what you can try to do is to linearize the numerator around 0. There is a similar argument around pi. So if you do that, so you say that because of this, so this is a cancellation. So because of the cancellation, this is essentially p times dpf of 0. Okay, this is a bit dangerous, so let me do like this actually for p small. The point is that the derivative of f is really divergent as p to 0, f to infinity. So the derivative, so notice, I won't write the exact, of course you can just write the exact value of this derivative, but just to understand where is the problem, let me discuss dimensionally the behavior. So dpf of 0 is something like, what should you do? So remember, this is essentially linear around 0. So this is a bit like, roughly speaking, k plus q minus p. If you derive with respect to p, here you get a 1, this last term is replaced by k plus q minus p squared. So this is roughly speaking something like for k and q small. This is essentially, dimensionally speaking, k plus q squared. So here I'm writing just dimensionally the pole-like divergences of this object. So remember, here we're in 2 dimensions. So roughly speaking, you have d4 something in the numerator, and you have 1 over something to the 4 downstairs. So this is logarithmically divergent. So if you put a p, this is like log p. Okay? So this is really there. So if you compute it, you really get a logarithm with a specific prefactor. If you're patient, you can compute it. Okay, I was not patient this weekend, but you can really compute the prefactor here. Okay, but then this thing here is not really okay, because you see this dp. So this sort of chain like this. Well, term by term is convergent. So the logarithm p of to the n is integrable, but it's not. This is like there is an extra n factorial, so which is not very nice. Why is not nice? Because essentially there is you already, so here there was a 1 over n factorial, but you already paid 1 n factorial by reordering each guy next to the one you're contracting. So 1 n factorial is eliminated that way, and you have an extra one here. So at the end of the day, you get the sum. So each guy after this cancellation is finite, but the sum of those is divergent, at least if you put absolute values on things like this. So there is really a problem. So the problem is not as serious as you think at the beginning because of the cancellation, but you have to do something. Let me suggest a possible strategy to get out. This is not the true story, but it's almost the true story. So what you can try to do is to say that the sum over all the chain diagrams, so here n is the number of these bubbles, is something of this sort. So it's something like, again, let me write things a bit roughly. So I don't write the n factorial, because that has been cancelled by the permutation I needed to put each guy next to the one that is contracted. But I write formally the result of this. Now, if you now you proceed blindly. You say, okay, this is a geometric series. I resum it, and this is alpha log p. Of course, there will be a constant. I'm not writing the constant properly. Okay, this constant c is the prefactor here that I was not so patient to compute. Now, if you're lucky, c has the right sign. So if c is positive, now this guy downstairs is larger than 1. So this is smaller than alpha. Sorry, here there is there is something wrong. It's alpha to the 2n, because each bubble has 2 alphas. Okay. this is also important. Not here. Yeah, maybe here. Okay. And now this is fine.
Don't you want C negative to make that work? Because you already have
D is almost 0.
Oh, sorry. Right, thank you.
Okay. I wrote it that way. So. Okay, and in fact, if you're patient, you compute C is positive, so you're in, after all, you are in a not so bad situation. But you see that what you did here was not really allowed, because you're summing a geometric series in a situation in which, in general, log T may be much larger than 1 in general. So this should be justified, and not only that, but you have to take into account that if you go to higher orders, here you get higher powers of the logs. So you have you start generating a lot of logs, and a priori it's not really clear what will happen. So let me anticipate that this log, and actually the even higher order logs that you may get in similar way, should be resummed using a sort of geometric series like this. And at the end of the day, what they will produce is will be summed together with the propagator. So we'll. And the result of this resummation will give you something of the following form: P to constant lambda square. So if you expand, so you will generate a critical exponent. If you expand in Taylor series, you will get P times 1 plus lambda squared log P.
So alpha and lambda
Are essentially the same. Alpha is e to the lambda minus 1, so we'll get confused in the following. It's the same as. So this is sort of the lowest order appearance of an anomalous critical exponent in the propagator. So this hints to what will happen later. I hope I will get to the point. So these logs are the signature that something serious is happening. So you try to perturb around the theory that as a propagator 1 over p. If you proceed naively, you find divergences, but if you put together in a smart way these divergences, you manage to reinterpret the theory in terms of a dress theory in which the propagator, instead of having a pole singularity 1 over p, has a strange singularity 1 over p to the 1 plus lambda squared.
So may I
Yes.
ask a question here? I remember the results. Would there be a staggering factor in front of that? I mean.
Yeah. Not in front of the propagator, but of some observables, because of what I will now discuss. So the staggering prefactors are due to the fact that the propagator is not exactly 1 over p. There is a singularity in 0 plus a similar one in pi pi, and pi pi in real space looked like minus 1 to the x oscillating prefactor.
If I remember right, there was a leading term which had a 1 over x behavior, and then there was an oscillatory term which had this kind of behavior.
Okay, that was in the result stated by Fabio last week. Yes. Yeah, the final goal, I'm not sure I will really get to the full proof of this. I hope you will, after this week, you will appreciate that the statement is very non-trivial, at least. And I'm not sure I will be able to give the full proof. So the statement was about, for instance, the
that was the dipole piece, yeah.
So this is an edge centered at x of type R. This is an edge of type y centered at y of type R prime.
So this involves 4 Fermi fields.
This involves 4 Fermi
Yeah,
fields.
yeah, yeah.
And there are 2 contributions. One, which is of this form. Real part of I don't have the notes here, so it could be slightly wrong, but don't completely trust these factors, but this just to give you the idea. So, and this is not these are somehow 2 different statements in the sense that you first prove something of this sort with an analytic prefactor here, an analytic prefactor here, and an analytic anomalous critical exponent here. And then you also show, and these guys are, this is 1 plus order lambda. This is 1 plus order lambda. This is 1 plus order lambda. And this is 1 over distance cubed, roughly speaking. And moreover, you have this thing. So this was the statement that in principle we would like to prove, but I don't think we will get there. Here, this critical exponent I'm mentioning here is not the same as this. Here you have 2 pair of Grassmann variables. These are these are at coinciding points. So this is like a density-density interaction. So the critical exponent appearing here is one of the critical exponents of a vertex function, and here there is no critical exponent. Here I'm saying, so there are 2 vertex functions, one with the same omega indices, one with opposite omega indices. In the Turing model language, one is the density, one is the mass. The mass critical exponent is non-zero. The density critical exponent is 0. Not only 0, but there is a special holomorphic structure here. And this is very important. A statement like this goes well beyond the kind of statement that allows you to resum. So this is a product of a lot of steps. You first prove that in general you could have 2 different critical exponents here and here. Then you prove that one of the critical exponents is 0. Then you prove that not only 0, but you have a special holomorphic structure. But this, I think, goes beyond what I will be able to do in this course.
So the exponent you're finding there is not really related to the new.
No, of course it has a connection, but it's not equal to that. So this is the critical exponent for the propagator, the one related to the wave function renormalization. This is the mass critical exponent.
Are you going to explain how this implies this height fluctuation formula that Fabio promised to prove but didn't?
Maybe not now, because I didn't even prepare the details. So maybe we can make an appendix for those who are interested.
Just after the talk I can explain.
Yeah, maybe after a talk we make a 15-minute session with the. Yeah, because if I do it at the blackboard without a reason to occupy all the time. Okay, so these are the kind of things one want to do. There are other logarithmic divergence a priori that cannot be resummed, not even formally in this way. So these are the chains of sausages, for instance, are an example of this that were also mentioned last time. This, or better, the generalization of this cannot be resummed in such a simple way. So the way out, so this a priori produces other log p to the n factors. The good thing is that there is a cancellation also here. That shows that even if a priori this is log p to the m, it's better than that. This is the vanishing beta function cancellation. So the key to have even just hopes, one has to show some cancellation and make some resummations. And in order to be able to give mathematical sense to all of this, we want to be able to check for cancellation, make resummations before ever getting to something like a geometric series of alpha square log p to the n. Because if we're at that stage, whatever we do involves resummation of divergent series. So we want to resum before we get to the problem. So the idea is to proceed in a multi-scale fashion, as suggested by Fabio at the end of last talk. So instead of integrating all that you have to integrate, you first start with the cutoff theory. You don't allow momenta smaller than something. If you do that, then the log p is not divergent. It's bounded by the log of the lower cutoff. And then the analog of this is convergent. So the idea, you first start with a cutoff, you identify the potentially divergent diagrams, you resum them, then you go to next scale, and you hope that the procedure converges. Okay, so let me now give more details about this multi-scale procedure. So this was this is something that Fabio started to discuss last week. I will start essentially from there. Okay, so we have this propagator that has in momentum space. Remember, this G was dk and there are these two singularities. So this is K1, K2. There are these two singularities at 0, 0, and pi, pi. So I want to define a sequence of cutoff theories in such a way that our real theory is the limit of the cutoff ones. So to cut off, we want to somehow exclude set of momenta in the vicinity of the two Fermi points. So as a preliminary step, it's convenient first of all to isolate from G the two terms that are singular in 0, 0 and pi, pi. So we do that. This is something that Fabio did last time. You can introduce first of all two characteristic functions. Well, actually, smooth version of characteristic functions that sum up to 1. These are sort of smooth version of characteristic functions of d square and the translated one. You insert it there, and you will write this as a sum over omega. This index was already introduced by Fabio last week. This labels the two singularities. This is singularity plus, this is the singularity minus in our conventions. So you have e to the, I can put this outside, I have e to the minus I omega. I don't know why I always get to the
the same function k or there are two different functions?
Yeah, the same, for instance. It's not important. But you can choose it to be the same. Yeah, I didn't, maybe I didn't write so cleanly. So you have g of xy is decomposed as the sum of two. These are called quasi-particle propagators, for an analogy with the Tiering model or lattice model. So I just write the same in a slightly clearer way. Remember that this mu of k plus p omega is essentially is a linear function of k. So this is the shift of momentum, you see. Okay, and this is in general a staggering prefactor. In our special case in which p plus is 0, it means that for omega equal plus, this term is not there. And for omega equal minus, this is just minus 1 to the x minus y. And this is one of the staggering prefactors that produce the staggering prefactor down there. Okay, so now this is this thing here is called g omega. I have to use the smaller equal to 0 refers to a scale that index will make sense soon. So now we start decomposing in scales as Fabio already started to do last time. Okay, so here I want to write this as a propagator supported on momenta of size 1 plus a rest that is the sort of the contribution from the singularity, in particular from momenta that are supported on momenta smaller or equal than 1/2, and then I will dive to it. So I just add and subtract chi of 2k. 2 is just a scaling parameter. You could choose it. I think this is what is called was called L in the conventions of Gordon. For those of you who were at the workshop at the beginning of September. Okay, so this is called f0. Okay. This is a function that, as a function of absolute value of k is whatever, is centered around 1 and leaves, I don't know, something like this. Is a bump. And this is, well, it's the same as chi, but computed at momenta 2k instead of k. So correspondingly, I will think of this as g0 omega plus g minus 1 xy. Now, this guy here, you see, as is the Fourier transform of something that is singular at 0, but multiplied by a characteristic function that cuts the small momenta. So this guy is very well behaved. So morally speaking, this behaves like whatever, constant e to the minus in absolute value. Okay, this is an issue that was raised last time. So depending on the regularity you choose, this exponential could be a stretched exponential or faster than any Python behavior. This is not important at all. So I will write this just to indicate this decays on scale 1 very rapidly. I mean, depending on the specific choice. So for instance, for technical reason, we choose a cutoff such that this is a stretched exponential, but this is really not the point. This guy here, you see, this is almost the same as g smaller equal than 0 up to rescaling. Why is that? Because mu of k plus p omega is almost linear. If it was exactly linear, then you could scale out the 2. Okay? So up to terms that are very small when you go on with the procedure, this is essentially 2 to the minus 1 g smaller equal than 0 2 to the minus 1 x. Okay, and when you go on, as you may imagine, this 2 to the minus 1 will become 2 to the minus 2, 2 to the minus 3, etc., etc. Okay, so if we do so, now we use the addition principle that Fabio introduced last time. So this is the same kind of addition principle we have for standard Gaussian integrals. It's valid also for these Grassmann integrals. So we had this object we were interested in, e to the v of psi. Remember, v of psi was nothing but minus 2 alpha sum over x psi plus x psi minus x plus e2 plus minus x minus e1. This is what we are interested in computing. Let me just rewrite. So first of all, we want to rewrite G as a sum of as a sum of 2 g omegas. So let me notationally indicate the step here. So here I'm just re-expressing everything in terms of the two fields supported in the vicinity of 0, 0 and pi pi. Next, I rewrite g smaller or equal than 0 as that. So this becomes this. Okay, everything clear? So I'm using this addition principle that Fabio already introduced last time.
So you need a sum over omega, maybe?
Yes, yes. In a minute I will drop this omega index. I mean, just to yeah. So this should be the set of the two omega fields. Other questions? Is it clear what I mean by this? I mean, it's important it is, otherwise from now on.
Can you remind what deep size with the upper suffix -1 means?
Yeah. This is just okay. This is just an index to say that these two guys are independent. This is by definition zero. The psi is the Grassmann Gaussian integration that by definition has propagator that is diagonal in the omega index and has propagator G0 omega x1. And similar for p smaller equal than 1 is the guy with G smaller equal than -1. And so I added an apex 0 and smaller equal than -1 just as a label for the two independent fields. And here I write, so I'm just saying that if the propagator is the sum of two propagators, the integral with respect to the Gaussian reference measure of a function is equal to the iterated integral of these two independent Gaussian measures for the function computed at the sum of the two fields. This is really the same as the analogous statement for Gaussian measures. More questions? Okay, now we start with the first step. So the first step is the one that Fabio started to discuss at the end of last lecture. So you defined, I use a slightly different notation, not very important. I let I integrate, re-exponentiate the result, and the result I call it v minus 1 of psi, with a notation that makes apparent that this is the analog of v of 0 on the next scale. I isolate explicitly here the term that is independent of psi. So there will be a vacuum term independent of psi this is a first contribution to the pressure. And then something that really needs to be integrated. In the notation of Fabio last week, this was included in this, but this is okay. Just to say that this you can put on a side, and then you have to continue computing this. Okay, how do you compute this? This is also something that Fabio started discussing last week. Let me remind it. So. L squared e minus 1 plus v minus 1 psi is equal to sum over n 1 over n factorial, the expectation with respect to the measure G0 of what? So this is exactly what we had before. Yeah, so let me write two steps, sorry. So this will be V0 of psi 0 plus psi n times. So if you remember what is V0, this is the same that I already wrote. Okay. Partially this is symbolic. This is very similar to what we had before, with the only difference that now there are some omega indices attached to the legs. So So this represents psi plus, psi minus, psi plus, psi minus, and now it has an omega index attached. Okay? Not clear?
But is it psi 0 plus psi plus?
And there are also some staggering prefactors.
Your vertex, is it psi 0 plus psi plus? You have a psi super 0 and a psi.
Yeah. In fact, each of the legs. Now, so now this is symbolic. I will clarify. So now each leg, first of all, is represent the sum of the two. It comes with upper plus minus index. It comes with a lower x1 plus e2, x1 minus e1 index, with an omega index that arises from the decomposition before. And and there are some staggering prefactors, some e to the I p of omega that arise from decomposing the psi field. So this I don't write everything, but I hope it's clear.
A completely stupid question. Why is it all of a sudden minus 2 alpha rather than alpha?
Because there was a minus 2 alpha from the beginning. Maybe I didn't write it. So it was minus 2 alpha sum over x. Okay. Yeah, maybe it's not very useful to be precise only in this term and not in the other. So let me write down. I mean, it's not very useful. Okay. Now I have to produce all possible terms. I have to sum over the choices. This is also something that Fabio mentioned. For each leg, I have to choose whether I pick up a psi 0 or a psi. So I choose, so the psis are those that are not integrated, the psi 0 are those that are integrated. So I fix those, let's say that the blue one is psi. So I choose some legs not to be integrated. And all the others should be integrated with the rule that the graph formed by these other white lines should be connected. I don't know, something of this sort. Each of these white lines is G0. Omega. Okay?
And now you can draw E0 because you have now taken the expression.
Very Okay, so at the end of the day, I get that v minus 1 has the following general form. So this is n larger than 2 and even psi plus x1 omega 1 psi minus x2 omega 2 plus xn minus 1 omega minus 1. Maybe I should have, yeah, okay. Sorry, this should be the blue guys. Okay. Times something which is labeled by all these omegas, by all these x's. This is the kernel with given number of external legs. So again, maybe n is a bit unfortunate. Let me write it as L, because otherwise it gets mixed with the order. Yeah, maybe this choice of colors was not that's not so good. Let me redo it. So this is the blue guy. These are blue guys. Okay, this is too much, you say. Okay, anyway. Okay, these are blue guys. So the blue guys are the external lines. This is the value of the contraction. Actually, to be fair, if written in this way, is the sum of all possible diagrams with the given number of external legs and given labels on the external legs. Okay, this is just a symbol. We would like to say that these kernels are well defined and essentially local. So this is what I would like to say. So we start at the 0 step with something that is very local. We just have a quartic interaction that lives on a plaquette. We integrate, we get new effective interaction. Now it has all possible number of external legs. It's not quartic anymore, it's an arbitrary number of steps. I hope that this is essentially local, even if not exactly local. So let's try to get a feeling of why that should be local. Okay, how can I understand? So let me discuss, for instance, the L1 norm of that guy. And next I will comment about the fact that you can easily extend the computation to a weighted, exponentially weighted L1 norm. So is finite L1 norm. So to prove it, let me start with, I start with a strategy that is not a posteriori the correct one, but again I try to prove this. So how do you do? So the L1 norm I'm using, of course, is normalized to one over L squared, because you have to anchor somewhere these guys. Okay, there is translational invariance. So if you sum over everybody, you get a trivial overall L squared factor that I'm dividing here. So this is what? This is smaller than one over n factorial alpha to the n, some constant to the n that comes from the summing over all the choice of the index. Maybe it's 2, maybe it's slightly more. Then I have sum over ways of contracting such that contraction is connected. And then for each contraction, I compute a bound for the L1 norm. So one possible way is the following. So I want to sum over all the so let's say x1 is set to 0, which I can always do by translation invariance. I have to sum over all the other differences. So how do you do? I use, in order to sum over the differences, I use a subgraph that minimally connects all the vertices. So in any contraction I can think of, I select a minimal so-called spanning tree, a minimal set of lines that is enough to make the vertices connected. Then there will be some other lines that are outside the green guy. Okay. Now I can bound these guys outside the green line just by the L infinity norm. I don't really need that. And then I have the guys on the spanning tree. please ask me if this is unclear, because if it is unclear, this is one of the things that will be used hundreds of times in the next 2 lectures. Is it clear, this way of bounding the L1 norm of the diagram? Okay, good. So yeah, let me also add an L to recall what is the number of external legs. Okay, so now, okay, at the first step, everything is of order 1. I mean, this is order 1, this is order 1, these are just constants. But let me track what are the, so here I'm just using the number of green lines is n minus 1. This is the number of, minimal number of lines you need to connect. This is what? Is total number of original lines minus those that are external, divided by 2, minus the guys on the spanning tree. Okay. Okay. So this this looks good, and this kind of bound will come again already on Wednesday and in the next 2 lectures. Okay. Now we are left with this thing here. This is not very good. So here the number of ways of contracting these lines. Unfortunately, you cannot find a bound that is qualitatively better than n factorial squared. Exercise, so think about it. But this is not very surprising, because if we do things like this, we are not really using the Grassmann nature of the variables. The bound would be equally valid for real Gaussian variables, for which it's known that it's known that the series is not analytic; it's just asymptotic or summable. So it's no surprise that you get an n factorial squared here. So there is a combinatorial problem. This okay, but this fortunately has been solved by the following idea. So I try to conclude today with this important idea. So the idea how to take advantage of the fermionic nature of the field. So I have some external guys. I proceed as follows. I first I make before getting the norms, I reorganize the expression I started from in the following way. So I first sum. So remember, I originally VW1 was something like sum over contraction, ways of contracting. These in the physics language are called Feynman diagrams. Of the value of the contraction. So this is what we originally have. In this formula, I just put, in order to get a bound, I put the absolute value inside. But this is not a good idea. So I want to find an alternative rewriting of this guy. So the alternative rewriting is the following. Instead, I sum over these ways of contracting morally in this way. I first sum over all the ways to minimally contract. So I make sum over minimal contraction. This is, if you like, a sum over the choices of the spanning tree. And then I keep all the rest together. So all the rest is, I keep together all the contractions of the fields I'm left with. But those form a determinant, precisely for the reason I mentioned at the beginning. So I get, what do I get? I get product over the green lines of the propagators of the green lines. And then I get the determinant of what I'm left with. if you re-expand the determinant, you get all possible values of the Feynman diagrams with their signs. But the good thing is that if you do this way, the determinant has a much better, so the determinant can be bounded morally by the maximal eigenvalue to the power dimension. So this is maximal eigenvalue to the dimension of the matrix. And the maximal eigenvalue, due to the structure of Z0, this is essentially the same. One can show that this is essentially the same as the L infinity norm to the dimension. So you are gaining, combinatorially, you are gaining a lot. You are gaining a factorial because you regroup together all these guys. So the sum over the minimal contractions counts how many trees you can construct, and these are n factorial. And here you get a constant to the equal and constant to the n. So if you use this improved expansion, you get number of trees and then you get this. And then you get that if you integrate just the first scale, so you don't have infrared singularities, the potential you're producing is analytic in the original interaction. So note that this is a very special feature of a Grassmann theory. Again, if some of you was at the workshop first week of September, there were two courses by Antti and Gordon Slade in which they hinted at the fact that one big technical problem in their story was to control the large field estimate, truncations of the series, control of the rest. Here in this context, you don't have any of that. You can expand everything, at least if you have a given infrared cutoff, and the result is an analytic function. And thanks to this determinant resummation here. Okay, here I cheated a little bit because the determinant resummation does not go simply like this. If you did something like this, you would have some overcounting of diagram. Because if you first sum of all possible ways and then contract all the rest, there would be a number of diagrams that would be counted more than once. And they would come with signs, so one starts to worry. Fortunately, there is a correct version of this due to David, among others. So this is slightly wrong, but morally correct. The really correct formula is this one. I refer to this as the determinant BBFK formula for Battle, Bridges, Feather, Bush, and Kennedy. One could add maybe some more letters. But,
You'll say with us
Okay, anyway, I usually write BBFK, but I hope Malek and Alessandro. Okay, anyway, so there is a correct version of this that is almost this up to some interpolation. So there is the correct version is the following. So if you have in general the truncated expectation of group of fields, so psi p is now product over some indices of psi and these indices are ordered because these are Grassmann variables. You have the order is important. So this is just a monomial. At the first step, we just have a quartic guy here, quartic guy, quartic guy. At later steps, we may have higher power. So let me just write what is the general formula. So this is sum over the spanning trees. So these are minimal ways of connecting these guys. This means that you pick up in all possible ways one field, okay, in this example, two fields from here, one from here, one from here, and then you decide a connection among the groups. So let me. There is a sign, no, alpha is not sigma t, plus minus 1 that depends on permutation. Product over L in T of G0 L. Okay, this is a symbol for the propagator with its indices on the line L. And then you have almost this guy. You have the following, to be precise. You have a probability measure of the determinant so T is a collection of T, J, J prime, J prime between 1 and n. So these are labels for these groups, and T, J, J primes is a variable associated with a pair of these guys. This, each of these variables is in 0, 1. This is a probability measure. So the total integral is 1. And G0 of T xi yj is just equal to, well, let me write I prime. Is Tj j prime G0 of xi x y prime. Where, I mean, so xi is the label of some field coming out of Pj. Yi prime is the label of some field coming out of Pj prime, and this is the label, this is the T labeled Jj prime. So J and J prime are the labels of the two groups. J prime. Okay? So this is just an interpolation parameter. It's between 0 and 1. So the infinity norm of this guy is exactly the same as before. So for the purpose of deriving this bound, nothing changes. Because you get here the L infinity norm of the interpolated guy, but this is, you just replace everything by 1, and this is the same as before. And now you have the, after you bounded all the t's by 1 to the purpose of this bound, you're left with the integral of the probability measure, which is 1.
What was the sigma t?
Plus minus 1. Depends on the, is a overall permutation, contribution from the permutation that depends on the choice of t.
Okay.
Again, I drop it for the purpose of the bound. So this is the correct formula. But it tells you that for the purpose of these bounds, you can equally well think in these rough terms, and it's exactly the same. And I think I will stop here. Okay. Now, whoever wants can stay for the computation of the variance.
Any questions?
How is this view defined?
Okay, so yeah, I don't plan to discuss the proof of this formula. It arises. Okay.
There's a fundamental theorem of calculus.
It's a just smart way of using the fundamental theorem.
If you're curious at some point, I can
The point is that it would take an extra hour by itself, so I don't think I will. No, I will not do it.
I might be able to do it quite a bit more quickly, but.
Quick, okay, very good. Okay, I think. For me, it takes 1 hour, but I guess it's quicker.
Yes, you have published lecture notes where this can be found.
Well, that's right. There are some published lecture notes in 1984 where something like this can be found, but if I were to do it again, I would do it much more, much better.
Now, on Friday, Fabio was drawing some trees to do this calculation. Is this the way that you actually do it?
No, these are not the same trees, so these are conceptually
No, I
different
know,
trees.
but he was drawing trees to
Yeah,
represent
I was
the
hoping to
terms.
get these trees arise when you iterate this. So I was hoping to introduce them today, but we'll introduce them next. Yeah, slightly more specific, if you like. So after the first step. So after the first step, we have this v minus 1. So v0 was, roughly speaking, this guy, okay, 40 guy. V minus 1 now is a series of thicker dots of all possible orders. And if you look inside, if you zoom, here there are all possible family of diagrams with a certain number. Okay, so now you iterate. So v minus 2 will be given by a sum of contractions on scale minus 1 of these thicker guys. So here, now I contract, these guys are minus 1, and if I zoom, each of them will be given by a certain other number of guys on scale 0, and then you iterate. So we essentially, thanks to this determinant formula, we group together a certain family of diagrams that are labeled hierarchically by a certain number of labels carried by these guys. And to keep track of this, it's convenient to use this those trees. So those trees are described this way. So I have here, say, 1 to n. And I draw an exiting line from this dot. This dot represents the action of e to the minus 1. Now, inside each of these, there are, I don't know, 2 guys here, 4 guys here, and whatever. 3 guys here. So I indicate for each of these guys, I indicate then, and now these correspond to E0. And I attach some labels to all of these guys. So for instance, here I say how many external fields I have here. So here 4. I say how many external and so on. So it's convenient to keep track of these indices in terms of these trees that encode this hierarchical organization of this family of diagrams. So these kind of trees must not be confused with these other kind of trees that live in a very different space. Okay, I guess we're done. If anybody is interested, I guess everybody can go to lunch and interested people can
The
stay.
computation of the variance
Now
makes,
maybe we leave a
Yeah,
5 minutes
yeah,
break.
yeah,
So
okay. but makes you feel in harmony with the universe. So it's a very nice computation.